what remains is the simplification of that. Okay. So let's take a look. So now, this is the question. And as I said, we want to use this formula. So we start with this formula. S is equal to EZ. S is equal to mu C omega naught A pi sigma 1 minus I n cross transverse at the surface. Okay. Now, then we want to use this formula. We want to use this formula, except we put this inside here. So we have partial E T partial Z minus transverse EZ is equal to minus I omega naught mu divided by C HT. Okay? And the E transverse, sorry, I have written down before a formula for E transverse, and now I've erased it, so stupid. Yeah? So I have to write it down again. So this EZ is equal to cosine x of y cosine P pi Z divided by D. E transverse is equal to minus P pi gamma square sine P pi Z divided by D. And HT is equal to I epsilon C gamma lambda squared cosine. Okay, so we have recopied these formulas, and now I'm going to use the E transverse, which is right here, and I differentiate respect to Z, and what do I get? I get this is equal to minus P squared, pi squared, D squared, gamma squared, cosine P pi Z divided by D. Okay. And this is the, so you have EZ is equal to this. So the transverse of EZ is equal to cosine P pi Z divided by D. So we have minus cosine P pi Z divided by D, and this is equal to minus I omega naught mu divided by C E3 cross. And these can be combined, of course, and I'm just, and the minus sign can be changed to the plus sign, and this whole thing can be written as 1 plus P pi squared, D squared, gamma squared, to I omega 0 mu C on E3 cross HT. Now, let me draw a picture of the boundary. So here is the boundary, and here is like H transverse, okay? And here is E3, and this is the normal direction. So from this, we do two operations. So we cross this into E3, and this, in fact, is along the normal direction. Why? Because this psi is along the z direction, so it must be only the normal derivative is not 0. So we cross this into here, and then after this, then we cross n into the whole thing. Okay, so if you get the cross product directions are all correct, then, and this, you recognize, this gives you the total wave vector square divided by gamma square. So the whole thing, and we move this I to the other side, so the whole thing is minus E3, okay, I C divided by omega naught mu, omega naught square epsilon mu, divided by gamma square C square minus partial n, and this is equal to n cross h of t. So this is a net effect. So we can essentially put this over here plus over here. So now we see we can have an expression to replace the n cross h transverse. And the replacement process essentially tells us that this, okay, we can, that this is psi. So psi at S is equal to partial psi, partial n. We have 1 minus I, and then we multiply by I, and then we have something, we can always write the delta, and then something I. And this gives me 1 plus I. And essentially, we have this expression. So F naught is something that you can figure out. But these constants are not important right now. Are not important. Because you can see we are only looking for behaviors or the rules that govern. So I want you to come away from the past hour or so with a remembrance of the Q factor and how you can read off the Q factor and the omega 0 from the experimental data. Okay? So these are the most important things you should do. If I had carried out all these jugglings, mathematics, without telling you where I'm going, you'll get totally confused. You think that's useless. Okay? So I want you to know that there is something to it. So for the last few minutes, I want to say a few things just to a very simple problem. on a waveguide, which is a dielectric sort of fiber, dielectric fiber, cylindrical fiber. So you can regard this as a cylindrical fiber, and we can say the outside, inside, so mu epsilon inside is equal to mu 1 epsilon 1, and outside is equal to mu 0 epsilon 0. So usually outside is just 1. You know, optical fiber is now is really incredible. Besides, of course, the widely used for communication purposes everywhere. Now we have optical fiber coming to our homes for TV and for your computer, for networking, everything. But they are also now used for operations, yeah, surgical operations. And how do you do that? In fact, it's very clever how they do that. You know, it's called the photonic crystal fibers. You know, photonic crystal is essentially, suppose you have holes. So suppose this is the optical fiber. And inside, you have a big hole. And surrounding, you have small holes. And these holes are all the way through, okay? Small holes. And they are arranged periodically. So the purpose of such a fiber is that you can transmit very high power laser light of a particular frequency through the central big hole. And why you want to make a photonic crystal of all the smaller holes on the side? Well, it is because it's arranged in such a way so that at the frequency of the laser light that goes through the central hole, it sees the surrounding as a band gap. You know, it's where it's a band gap. And when you have a band gap, there's no state. So it cannot penetrate into, it's totally reflected. So it's totally confined within the central hole. So you say, well, why do you want to do that? Can you just use the optical fiber just to guide the laser light? No. The reason is, if you want to do operations, this central hole has to carry extremely high power laser light. So with one pulse, you can sort of cut the tumor or something like that, or to seal the blood vessel from bleeding. So if you don't use photonic crystal fibers, the power used in the central thing can melt the glass, and that would be disaster, right? So the only way you can do it is to go through air in the middle. And that's very clever. And now, for example, you can do these operations very remotely by cutting a small incision, like 1 centimeter. They can go inside, and they have robotic arms that can guide you. So now the surgeon, instead, standing beside the patient and do things, when the operation begins, the surgeon goes to the corner of the operation room and sit down at a console and stare into a stereoscope, and a robotic arm moves to next to the patient. And then they start the operation. Now the robotics arm can do extremely precise. And this kind of thing, the photonic optical fiber, is one of the technologies that's crucial to such operation for cutting. Okay? For cutting things or sealing off the blood vessels, so from bleeding, these things. And also they can do stitching in a very tight space, these robotic arms. It's very remarkable nowadays that how the medical technology has advanced. So you say, if you have an optical fiber that's very thin, how can you make these holes regularly, over a long distance? That seems to be impossible. Okay. Do you know how? What's the technology? Actually, very simple. It's a very rudimentary technology. It's a technology called the ramen technology. Have you seen how people make ramen? Yeah. This experience. It looks very simple, but if you do it, you'll be very, you will make a mess. It takes years of experience. So what do? Is they have a big thing, and when a big thing, you make holes. It's very precise and simple. Cut, and then you pull longer, and they become thinner and thinner. And this is called a conformal deformation. Conformal. So when they become thinner, everything becomes smaller in a cross section, but with exactly the same scale ratio. Therefore, these holes become smaller, and become longer. So that's so the Chinese ramen has a lot of technology behind it. So it's a very simple, but when you think of this, it's very clever, right? But that's the way they do it, basically. Of course, you have to pull very slowly and uniformly, or things like that. Okay, these are the besides what I'm talking about. But what I want to emphasize is fiber optics is now important not only for communication, but also for medical and other uses. Okay, so mainly is for transmitting frequency, the electromagnetic signal and electromagnetic power. Okay, these are the two things, the fiber optics. So we have this, and then we can write the transverse, and we have mu epsilon omega square c square minus k square. And we will have the E and B is equal to 0. So this is the total wave vector. This is the wave vector along the z direction, guided wave direction. And this is a transverse Laplacian, two-dimensional Laplacian. And now, I want to show you that gamma squared inside is equal to mu1 epsilon 1 omega squared c squared minus k squared. So this is always greater than 0. In other words, we want mu1 epsilon 1 greater than mu 0. That's clear. That's obvious. Okay? Because you want the inside n squared greater than the outside. So you can have total internal reflection. So I'm doing this problem for a very simple profile, namely a constant index refraction across. For the real fibers nowadays, they use dopings. So the index refraction can have a profile inside, like parabolic profile or step profile, many things. So it's not so simple. But in any case, we use this. And then outside, beta squared, the transverse wave vector outside has to be exponential decay. Okay. So we want this is k squared minus omega naught epsilon naught omega squared c squared. And this is 0. So we get the reverse, this is 0. So that implies beta is exponential decay constant outside. Now, because of these two relations, gamma and beta are not constant, are not independent. You can see that.